Okay, so good morning, everyone. Welcome to the morning session of this room. And there will be three talks in this room this morning. And I am glad to introduce our first speaker, Professor Yasuyuki Kawahigashi from the University of Tokyo. And he is clearly addressed as Yasu, as the title shows. And the title of his talk is Operator Algebras and Tensor Categories and Tensor Networks. Let's enjoy.
Okay, thank you very much. So I thank the organizers for this invitation to a great meeting. This is my third visit to BIMSA and also 20th visit to China. And I'm glad to see your great development in China every time. So today I'd like to talk about operator algebras and their applications to some problems in mathematical physics. So particularly about tensor categories and tensor networks. So tensor categories, I'll explain about this later. But sometimes with braiding or sometimes without braiding, they are increasingly important in mathematics and physics, like quantum field theory or condensed matter physics. So operator algebras, particularly the theory of subfactors initiated by Vaughan Jones, give powerful tools to study such categories. And particularly, I'll talk about the bi-unitary connection. I'll explain this notion later. This is some variant of quantum 6J symbols, which I also explain later. That naturally appear in theory of operator algebras. And this plays an important role in connection to tensor networks, which is important in applications to condensed matter physics recently. So the outline of my talk is following. So I first explain tensor categories and its connection to operator algebras. Then I'll explain what quantum 6J symbols are and then what bi-unitary connections are. Then explain bi-unitary connections and their relations to tensor networks, which is some graphical method to deal with lots of operations. Involving lots of complex numbers explicitly. Then I'll explain matrix product operators. That's a popular notion in condensed matter physics recently. And then that's related to two-dimensional topological order. Then I'll explain alpha induction, which is a certain induction machinery for something like a representation. So for classical representation theory, we have a notion of induced representation from a representation of a subgroup to a representation of a larger group. So we have some kind of induction procedure in this setting and the setting of tensor categories. Then finally, I'll explain some new results about flat connections and the Frobenius algebras. This is a recent popular topic in theory of tensor categories. Then I explain notion of tensor categories. So as a basic fundamental example, so consider, so we fix a finite group G, and then we consider finite dimensional unitary representations of this fixed group G. Then they produce some kind of category. So for categories, we have objects and intertwiners or morphisms. Then here, objects are given by these representations. Then between objects, we have notion of a morphism. So in this setting, we have an intertwiner space with home between pi and sigma. So pi and sigma are objects that are unitary representations of the same group. Then the intertwiner space is given by this thing. So T is a linear map. So this is so B is bounded linear operator, but here everything is finite dimensional, so boundedness automatic. So this is just a linear map from the representation space of pi to the representation space of sigma, which intertwines relations in this way. So T times pi G is equal to sigma G times T for all the group elements G. Then so this is a linear space. So the home space is a linear space in this setting. Then here we also have a notion of a tensor product of objects. So if we have two representations of the same group, we can make a tensor product of these two representations, which is again a unitary representation and which has a irreducible decomposition. Then we have some abstract axiomatization of this setting, and it's for the tensor category, because it's a category with tensor product among objects. So this is well, I don't write down the exact definition, but this is a notion of a tensor category. Then in this example of representation of a fixed finite group, because the group is finite, we have only finitely many irreducible representations up to unitary equivalence. And if we have this kind of finiteness, then we have a fusion category. So this is the terminology we use. So this name comes from a fusion rule in conformal field theory. And also, in the setting of group representations, pi tensor sigma and sigma tensor pi are trivially unitarily equivalent. In a general setting of a fusion category, we do not require this kind of commutativity for the tensor product, but in some nice extensions, we do have this kind of commutativity in a general setting with some kind of non-trivial commutativity. And this kind of non-trivial commutativity is called braiding, non-degenerate braiding. And if we do have such non-degenerate braiding, we call this one modular tensor category instead of a fusion category. And this kind of tensor category describes a new type of symmetry which generalize the classical notion of a group. And this kind of symmetry is often called non-invertible symmetry in recent papers in physics, like quantum field theory. Then I briefly explain a notion in operator algebras. So this is of course an algebra of operators, but here an operator means a bound linear operator on the Hilbert space. So let H be Hilbert space, so typically L2 of R. Then all the bound linear operators on H make an algebra, because we have multiplication, which is given by composition, and addition also. A subalgebra of B of H is called a C-star algebra if it is closed in the norm topology and the star operation. Then it is called a von Neumann algebra if it is closed in the strong operator topology, which is given by pointwise convergence topology on the Hilbert space and the star operation. So this strong operator topology is weaker, despite this name, than the norm topology. So being a von Neumann algebra is a stronger condition than being a C-star algebra. And of course, typically this multiplication is non-commutative, just like a matrix multiplication. But sometimes we can consider commutative operator algebra. And if we have a commutative C-star algebra, it is of the form C of X, where X is a compact Hausdorff space. And so this is a algebra of continuous functions, complex valued. And if we have a commutative von Neumann algebra, it is of the form of L infinity X, where X is a measure space. So general C-star or von Neumann algebras are kind of non-commutative versions of these function algebras. And also, if we have a finite dimensional operator algebra, it's just a finite direct sum of matrix algebras, n by n matrix algebra, Mn of C. Then Jones started a theory of subfactors. So just like in the classical group setting, we are interested in simple groups. So also we are interested in simple von Neumann algebras or simple C-star algebras. And in the setting of von Neumann algebras, a simple von Neumann algebra is called a factor. This is just a historic name invented by von Neumann. Then so factors are classified into some types. Type 1, n. N is 1 to up to infinity, including infinity. Then also we have type 2, 1 and type 2 infinity. And then also we also have type 3. So basically type 1, 2, 3, some with subscripts. Then in connection to mathematical physics, we often have factors of type 2, 1 and type 3. They are particularly common in connection to statistical mechanics and quantum field theory, respectively. Then Jones considered a Galois type theory for an inclusion of factors. So in the classical setting of Galois theory, we have a field and field extension. So we have two fields with inclusion, then we can consider the Galois group. And so this is a classical setting. So instead of a field, we consider an operator algebra. So we have an inclusion of two operator algebras, particularly factors. So one factor is containing another factor. n in M, this kind of setting is called a subfactor. So subfactor is containing another factor. Then in today's terminology, a new type of symmetry for this setting, which replaces the classical notion of the Galois group, is described with the tensor category. So instead of a group, we now have tensor categories, which describes a new type of quantum symmetry. Then also the celebrated Jones polynomial, which is not invariant. This is also understood in this framework of tensor categories. Then we also have mentioned that the notion of a superselection sector, which is a kind of representation theory in the setting of quantum field theory. So this is a representation of a family of operator algebras. And then this naturally produces a subfactor. So lots of different notions in different fields of mathematics and physics are naturally related to subfactor in a rather surprising way. That was mainly a discovery of Jones. Then, I explain how to study tensor categories in the setting of operator algebras. So, of course, tensor categories are abstract notions, so many people study them without using operator algebras, but we have some advantage of using operator algebras for concrete constructions or also handling of concrete problems in tensor categories. So we are interested in operator algebraic studies of tensor categories. That's our main object in this talk. So then we have three natural ways of realization of objects in the tensor category. So an object in our tensor category is some kind of representation of something. So that's the basic idea. Then this kind of representation is described in the following three ways in the setting of operator algebra. So if we have an endomorphism of a type 3 factor, then we can naturally produce a tensor category. So in this setting, we have a notion of a tensor product that's given by a composition of endomorphisms. So if we have two endomorphisms of the same algebra, of course, we can compose them to get a new endomorphism. And this is a notion of a composition or tensor product in our setting. And also, if we have a bimodule of a type 2-1 factor, so let M be a type 2-1 factor, some kind of operator algebra, then we look at an M bimodule. That is the Hilbert space with the left action of M and the right action of M. Then if we have two MM bimodule, we can make a tensor product over M. So this produces another MM bimodule. So in this way, from two MM bimodule, we can create a new MM bimodule through a tensor product. That's a composition or tensor product operation in this setting. These are rather easy to understand. But then we also have another notion given by a bi-unitary connection, which I explain later. That's some kind of family of complex numbers, just a finite set of complex numbers satisfying some actions. Then, so they are really finite dimensional objects, but then they produce tensor category through operator algebras. And then we also have a notion of a composition of bi-unitary connection that gives the correct notion of a tensor product in this setting. Then we have realization of a tensor category in this setting. Then, so in today's talk, we focus on the third method because of its connection to two-dimensional topological order. So two-dimensional topological order is rather new topic in condensed matter physics. So two-dimension means that we have just a large plane, and we have lots of something like a particle, which is often called a quasi-particle, some kind of excitation. And then these kind of particles move around on the plane. Then they have some kind of interaction. And this kind of interaction is given, described by a tensor category, or actually braided tensor category. And this is a recent hot topic in condensed matter physics, and they are described with this kind of bi-unitary connection, so finite dimensional, basically matrix. So that's an important aspect of this kind of application. Then, in order to explain bi-unitary connections, I start with some classical notion of 6J symbols. So this is a completely classical notion, but maybe not so widely known. So I explain something basic in this setting. So we fix a finite group G or maybe compact. Then we look at 6 irreducible representation, okay, unitary representation, pi 1, 2, 3, 4, 5, 6. Then we compose them in this way. So here we compose my tensor product 1, 3, 2. Okay, but here, okay, so 2 are common here. So this means that pi 1 tensor pi 3 is decomposed into, say, pi 5. So this is just a direct summand of irreducible decomposition. Here, pi 1 are common. So if we make a tensor product of pi 3 and pi 2, that contains pi 4 as an irreducible summand. So this means that here we have a tensor product of 3 representations, and here we first decompose the left 2, and here we first decompose the right 2. So by associativity of the tensor product, we can decompose these 3 tensor products in 2 ways. So first from the left or first from the right. Then after that, here we also apply the pi 2. Then we get the representation pi 6 as an irreducible direct summand. And also the same pi 6 also can appear here. Later we apply pi 1. Then these T1, 2, 3, 4 are just intertwiners between representations. And here we have pi 2 are common. So we have identity for the common pi 2 component. So this T3 is an intertwiner from pi 1 tensor pi 3 to pi 5. Okay. So in this way, we have from pi 1 tensor pi 3 to pi 2 to pi 6, we have 2 intertwiners in this way. Then if we start at pi 6, we can compose these 4 intertwiners in this way. So we take the star, we can reverse the orientation of the arrow, so we can compose them in this way, 4 intertwiners in this way. Then we get a self-intertwiner from pi 6 to pi 6. But pi 6 is an irreducible representation, so our self-intertwiner should be a number. So in this way, by composing 4 intertwiners, we get a complex number. So if we choose 6 irreducible representations, and if we fix 4 intertwiners, then we get a number. And this assignment of a number is called a 6J symbol. And here we say 6J because we have 6 irreducible representations. And in a classical notation, here I used pi 1, pi 2, so on. But in the classical setting, they used the symbol J for representation. So we have 6 kinds of J, and that's why they call 6J symbols. So, and also here, in a very nice situation, these T1, T2 intertwiner spaces are just one-dimensional. Then basically we have only choice up to phase. So basically we get a family of numbers. So that's why they consider this set of numbers and call it 6J symbols. But in general, we have multiplicity for intertwiner space. So the space of T1 could be multi-dimensional, but still finite dimensional. So we have 4 finite dimensional space, and if we choose one vector from each space, then we get a number. So in this way, we get a finite remaining numbers, and this is called a 6J symbol. This is a well-known classical notion. Then we can generalize this to our setting of tensor categories. But for making everything explicit, use the setting of bimodules. So here we have 6 bimodules, but now I use different notation. So A, B, C, D, X, Y irreducible bimodules over some algebra. So details don't matter. So we have just bimodules, and we have 4 algebras, N, M, P, Q. And then, for example, A is an MP bimodule. So this is a Hilbert space with the left action of M and the right action of P. Then we can make this kind of tensor product. So A is an MP bimodule, X is an NM bimodule, Y is a PQ bimodule. So here we can make a relative tensor product over M. So this is the right M module, this is the left M module. Then we can make a tensor product over M. Then this is the NP bimodule. And here we have a common P. Then we can make a tensor product of A and Y. Then this is an MQ bimodule. So after making a tensor product of 3 bimodule, we get the NQ bimodule. And then similarly, here, so we first multiply X and A, and we get irreducible bimodule C as a direct summand. Then we have a common Y here. So we have an intertwiner from X tensor A to C, that's T3. So we have just a user identity here. So we have an intertwiner here. And similarly, we have this map. So here X is common. So from A tensor Y, we have B, a direct summand of irreducible decomposition. So that's the intertwiner is given by T1. So this part, this is short, but this is the T1. So we have another thing. And also here, X times B produces D, and also C times Y produces D. So in this way, we have 6 bimodules, just like 6 irreducible representations. And we have, again, 4 intertwiners, and they are from finite dimensional home spaces. And then when we compose these 4 intertwiners in this way, from D to D, then again, by irreducibility of D, this self-intertwiner gives the number. So in this way, again, we have 6 objects, irreducible objects. There are only finite remaining. So we choose 6 of them, and then we choose intertwiners from each finite dimensional subspace. Then by composing them, we get the number. So in this way, we have a finite family of complex numbers, and they are called quantum 6J symbols. And we use the name quantum because something similar is used in the theory of quantum groups. Okay. Then now I talk a little bit about something else, but still this is closely related. We consider finite dimensional non-degenerate commuting square, which I don't give definition, but basically A, B, C, D are finite dimensional operator algebras. So they are all direct sums of matrix algebras. Then we have some kind of trace D, but it's not so important. This is a kind of inclusion of inclusion. So here we have A in B, A in C, C in D, B in D. So we have 4 inclusions. But we regard this as this is a basic inclusion, A in B. This is another inclusion of C in D. Then this pair, A and B, is contained in this pair. So this is an inclusion of inclusions. So then we have a natural notion of inclusion of inclusions, and we have some kind of nice characterization to properly grasp this setting. Then that's a notion of a commuting square. I don't explain the definition, but there is a natural notion to describe an inclusion of inclusions of finite dimensional algebras. Then an inclusion of finite dimensional fixed algebras gives a bipartite graph called the Brattley diagram, because here we have finite remaining direct summand. So we have each dot to represent direct summand. So we have finite remaining dots here, and we have finite remaining dots here. And then one summand is contained in another summand with some multiplicity. Then we draw edges with this multiplicity. So in this way, we have some diagram, just like this. This kind of bipartite graph. So we have one set of vertices, another set of vertices, and each vertex is connected in this kind of way. So this is a bipartite graph. And this is called the Brattley diagram because Brattley used this kind of thing for study of fifth algebras. Then, so here we have 4 inclusions. So one graph here, one graph, another graph, another graph. So we have 4 bipartite graphs arising from this setting. Then we choose one edge here, one edge here, one edge here, one edge here. So we choose 4 edges from 4 graphs. Then we can assign a number, complex number, just like the previous setting of quantum 6J symbols. If we choose 4 edges, like 4 intertwiners, then we get a number. And we can show that these numbers form a unitary matrix in 2 ways. So these numbers have to satisfy some kind of unitarity in some double ways. And then we can axiomatize these numbers, and we call it a bi-unitary connection. This bi-unitary means that so they are unitary. They produce a unitary matrix in double ways. So this is bi-unitary. Why we use this name. And this name connection comes from an analogy to this notion in differential geometry. So this graph is a kind of manifold, discrete manifold. Then this is similar to the classical notion of connection in some sense. So we use this name bi-unitary connection. Then I explain some relations between bi-unitary connection and subfactor. We start with the commuting square, this one, 0, 0, 0, 1, 1, 0, 1, 1. So this is the commuting square. Then we have a notion of the Jones basic construction, produce a new commuting square. So if this is the initial one, then we create a larger commuting square. This is a new commuting square. We can repeat this one, and we can repeat this process of basic construction indefinitely. Then we get two increasing sequences of finite dimensional algebra. Okay, everything is finite dimensional. We can increase, we have an increasing sequence of finite dimension. Then we can take a certain limit. So this is an increasing union of the first row. This is an increasing union of the second row. Then, so this is an inclusion of infinite dimensional algebras. But then we can make a certain completion called GNS completion with respect to the trace, where it doesn't matter if you don't know them. So in this way, we get an inclusion of infinite dimensional actually factors, von Neumann algebras. So A0 infinity is contained in A1 infinity. So 0, 0, 0, 1. So the limit algebra is a kind of 0 infinity, 1 infinity, and here is an inclusion. So in this way, we get the subfactor. It turns out that we do get the factor in this way. And also we have some finite Jones index, some kind of finiteness of the inclusion. Then we also can make a vertical basic construction. So this is a horizontal basic construction, but we can also make a vertical basic construction. Then we can produce a Jones tower, so 0 infinity. So this limiting algebra is 0 infinity, 1 infinity, 2 infinity, 3 infinity, and so on. So we get this kind of inclusion. Then, so that's one direction. Also, we have a converse direction. If we have an abstract subfactor, we can produce a bi-unitary connection for the other direction. So we start with the subfactor, some kind of finiteness condition. Then we can again produce a Jones tower. So from the initial inclusion, we can create a larger algebra, and we can repeat this one and so on. So we get a larger and larger von Neumann algebra factors. Then we look at the here some large algebra, and we have small algebra. Then we look at the relative commutant, which consists of all the operators in the large algebra, which commute with everything in the small algebra. And then it turns out that this is a finite dimensional algebra. Then if the initial subfactor is has some nice condition called finite depth, this is some kind of rationality in conformal field theory. Also in quantum group setting, this is something like a condition of being a root of unity. So which is some nice condition producing finiteness condition. If we have some kind of finiteness, then we can get the commuting square in this way. So we look at the m prime and mk. Then mk is contained in mk plus 1. So we have this inclusion. And also here, m is larger. So the commutant of m is smaller than the commutant of n in the same algebra. So we have this inclusion, we have this inclusion, and this inclusion. So in this way, we get 4 inclusion. And it turns out that this is a commuting square in general. Then Popper's classification theorem says that if you have some hyperfiniteness, which is a kind of approximation property by finite dimensional algebras, then this connection corresponds to this commuting square completely recovers the original subfactor. So classification of subfactor is reduced to classification of commuting square, which is also reduced to classification of bi-unitary connection. So in this way, classification problem of infinite dimensional inclusion of von Neumann algebras is reduced to classification of finite dimensional objects by unitary connection. So this is a great reduction of classification theory to finite dimensional problem. Then explain the next notion of flatness. This is a certain property of being canonical bi-unitary connection. So the quantum 6J symbols arise from associativity of the tensor product operation. So like in the previous thing, so we have x, a, y, three bimodules, x, a, y, but here we multiply the left two components. Here we multiply the right two components, and they produce the same thing, maybe naturally isomorphic. Then, actually, by my result last year, this kind of quantum 6J symbols arising from this setting give a general form of bi-unitary connection as long as we are interested in subfactors of finite depth. So it's easy to see that quantum 6J symbols produces nice bi-unitary connections, but actually they characterize all bi-unitary connections we are interested in. So in this setting, in this sense, basically a bi-unitary connection and quantum 6J symbols in this generalized setting, we are with 4 algebras, they are the same kind of thing. Then, but here we have a new thing. So we have 4 algebras here. But if two middle algebras, M and P, okay, if they are the same, then here as an A, we can take, so here we have M and M. Then here we have also M itself as an MM bimodule. And so if we regard M as an MM bimodule, this plays the role of the identity bimodule. So this is the identity object for the tensor product. So this one. Actually, this is not a Hilbert space, so we need a Hilbert space completion, but it's not important. So here for the middle bimodule, we have the identity bimodule. So if we have this identity choice, then this is a particularly nice form of quantum 6J symbols, and it turns out that bi-unitary connections is of some canonical form. If we can choose this one to be the identity, then we say this bi-unitary connection is a flat. And again, this name, flat connection, comes from an analogy to the notion of a flat connection in differential geometry. So this is some kind of discrete form of a flat connection. And also, yeah, actually this flatness is characterized by some property that a certain large diagram called partition function has a value 1. This property having a value 1 is connected to some nice property of a parallel transport, which is really similar to the notion of flat connection in differential geometry. And this is why we use this name. So this is the characterization of a bi-unitary connection in a general setting, and also this is the characterization of bi-unitary connection in some particularly nice canonical form. Then I briefly mentioned relations to two-dimensional statistical physics. So there's the notion of K-tensor, that's entirely elementary. This is just a finite family of complex numbers indexed by K indices. So AJ, that's a vector, that's a one tensor. And matrix is, entry is written as AJK. So this is given by two indices. So a matrix is given by two tensor. So one tensor, two tensor, the next one is three tensor, four tensor, five tensor, and we can consider everything. But in this setting, we are particularly interested in four tensor. That's important in the setting. So bi-unitary connection is a family of complex numbers determined by four edges. So this is a family of complex numbers depending on choices, four choices. So that's a four tensor. And this kind of four tensor appears recently in the study of topological order in condensed matter physics. And then here, this is a connection picture. So these edges. Then we have some, actually, there is some subtle definition because so this is a four tensor depending on four choices. This is a typical picture for representing the four tensor. But then we concatenate this one here. So next one, but here in the original setting, this index set and this index set are different. Then we cannot concatenate this picture. So in order to make a concatenation, we need some kind of reflection. This W prime is a kind of horizontal reflection. Then we can make a composition here. Then here, this set and this set are index set, they are the same. Then here we have C1, C4 are in the same index set. then we can compose or concatenate these four tensors. But this is just a matter of technicality. And also this has some normalization. These are some positive numbers given by a graph, so that's not essential. So basically, this is a four tensor, this is another four tensor, and this is a concatenation. And then this is a four tensor which naturally appears in condensed matter physics. So this kind of four tensor has been used recently by physicists in the last, say, 5 maybe years. And they are used to describe two-dimensional topological order, and their physicists are interested in explicit numerical computations of this kind of thing. So they are interested in this kind of structures in connection to, say, topological quantum computations. So quantum computers are really a hot topic in everywhere. And this kind of thing is expected to be useful for studies of some particular form of quantum computers, which are called topological quantum computers based on topological manipulation. So that's why they are interested in this kind of thing. Then they have this kind of construction. So this is a picture of four tensor. So here, this A is just a label. So we have four wires, so N1, M1, and here we have two wires. So this is a complex number given by four indices. This is another complex number given by four things. And we have concatenation like this one, and also we close this loop. Then basically, we mean that we multiply these numbers. So here we have k numbers. So we multiply k numbers. And then we have a summation over closed edges, just like a matrix multiplication. So matrix multiplication is this one. Okay. So this is say A, J, say L, B, L, K. So the matrix element is given by this one for the product. And here we multiply two numbers just like this. Then here we have common L, and we have summation over L. And here we have some closed wire, and it means that we have a summation over this part without label. So this summation over L is written in this way. So similarly, here we have no label, so it means that we have a summation over this one, this one, this one, this one. Then after summation, this part gives a number. So this is a coefficient complex number, and this is a bracket notation for N1, Nk. So these are just some numbers, index. And then here this is a bracket notation. So this is a rank 1 matrix, rank 1 partial isometry. So we have this rank 1 operator, matrix, coefficient, and we have summation. So this is a matrix, finite dimensional matrix, and they call this is a matrix product operator, because if we have three tensors for this one, then we get a vector from a similar picture, and that's called the matrix product state. That's very popular in condensed matter physics for last, say, 20 years. Then recently they consider four tensor version, and they call it matrix product operator. Then here we have summation. Then actually we need some coefficient normalization. Then we get a projection, and they call it the projector matrix product operator, PMPO. Then they study this kind of thing, and they are interesting studies of this kind of matrices in connection to gapped Hamiltonian. So that's a big main notion in condensed matter physics. And then they are interested in the range of gapped Hamiltonian. And then it turns out that the range of their projection, that's important. So this is a Hilbert space important in the setting. But it turns out that this Hilbert space is identified with something well known in subfactor theory, known as higher relative competence, like N prime in MK. So their Hilbert space and our Hilbert space in subfactor theory exactly correspond to each other. So in this way, we have a nice identification of their notion in subfactor setting. Then we have a lot of natural understanding of their construction in our subfactor theory. So this connects their theory and our theory. So that's yeah, my result last year. Then I now talk about some another topic called the Frobenius algebra. So suppose we have a subfactor n in M, that's our initial setting with some finiteness assumption. Then the nn bimodule arising from this subfactor gives a fusion category. So we can get M. So the larger algebra is an n bimodule with some Hilbert space completion. Then we can make a tensor product over n. Then we can so M tensor and over n. In this way, we get lots of n bimodules, and we make irreducible decomposition. Then in this way, we get lots of n bimodules. And if we have only finitely many irreducible n bimodules arising in this way, then we get a fusion category of n bimodules. Then among this fusion category, this M has some distinguished meaning. This is a kind of generator of the fusion category. So this is a nice thing. But then this is called an algebra in a fusion category in abstract setting because so M tensor M, so this n bimodule, so we make a self power over n. Then here from this to this, but then from this tensor product to that, we have a trivial, multiplication here. So if we have x here, y tensor here, of course, x tensor y, but then this is mapped to x just times y. Because this is an algebra, we have a multiplication. So this product operation gives some nice associative intertwiner from this bimodule tensor product to another bimodule. Then we have an abstract characterization of this kind of bimodule intertwiner or morphism in a tensor category. And then this kind of abstract characterization of such an algebra is called a Frobenius algebra because this is some kind of generalization of a classical object Frobenius studied 100 years ago. Then we also have a notion of a commutative Frobenius algebra if we have braiding. If we have a braiding, we can switch the order of the tensor product from x tensor y, we get y tensor x. Then we can switch the order of the product here. Then if we still have the same result, that's a kind of commutativity of the product operation. So we call it a commutative Frobenius algebra. And also this kind of commutativity is studied also in the context of quantum field theory, particularly conformal field theory in the operator algebra setting. Then this commutativity corresponds to a locality of an extension. So sometimes we say a local Frobenius algebra. This locality is arises from Einstein causality of observables in quantum field theory. So in quantum field theory, observables are represented by some self-adjoint operators. And if we have two observables, they do not commute in general. But if we have one object here, another object here, and they are space-like separated, it means that we have no interaction even at the speed of the light. Then we have no interaction, so two observables commute. And this kind of commutativity is called locality in conformal quantum field theory. Then we have a notion of alpha induction for endomorphism. So this is an induction procedure like a classical representation theory. So we want to produce a new object from an old object. So something like representation. So we start with some Frobenius algebra. We don't assume commutativity of a modular tensor category of say endomorphisms of smaller algebra. Then object is represented by an endomorphism of the smaller algebra, the lambda, the smaller algebra in the fusion category. Then we want to, so we, from an endomorphism of the smaller algebra, we want to find an endomorphism of the larger algebra. So the most natural thing is just an extension of the endomorphism. So we want to extend an endomorphism of the smaller algebra to the larger algebra. And this is not possible in general at all. But under existence of nice braiding and nice Frobenius algebra, we can make this kind of extension by this explicit formula. So this lambda is an endomorphism of the small algebra, and alpha lambda is an endomorphism of the large algebra. And actually, this depends on the choice of braiding. So we have plus or minus. This plus or minus depends on the choice of the braiding. So we have overcrossing, undercrossing. So this is a choice of braiding. Then we have some iota bar, some kind of morphism inverse, some adjoint, this is a braiding, something, this is canonical endomorphism, something iota bar. So details don't matter, but we do have some explicit formula for an extension of endomorphisms. So iota is the inclusion map, and iota bar is a conjugation arising from the Tomita-Takesaki theory, and this V is some nice symmetry. Then we have this formula gives the extension. So if X is the small algebra, that gives the same thing. And then the new thing is saying we just have one new element for large algebra, and that's mapped to something here. And this kind of thing was first defined by Long and Reren many years ago, and studied by Fenshu, Beckenhauer, Evans, and also with me later. So that was a hot topic many years ago, but we studied this kind of thing a lot many years ago. And then this has some new application in recent studies of tensor network. So we want to understand the alpha induction in terms of bi-unitary connection. That's a recent problem arising from the renewed interest in tensor networks. Then here we have the alpha induction here, alpha induction. Then these are some irreducible morphisms using A1, A2, A3, A4, and some kind of lambda mu. Then we draw something like a diagram we used for quantum 6J symbols, but somehow we have intertwiners here. But then here we have one extra step here arising from braiding. So here we have lambda and A1, but we switch the order. So A1 and this becomes just lambda. And also here we switch the order. And this comes from braiding. So this capital E plus this is a braiding operator. So we switch the order of the tensor components. So because of braiding, we can switch the order here, then we can naturally compose here. Then, so with this new part of braiding, this picture is similar to the diagram for quantum 6J symbols we had. Then we, again, here we have, so this is the initial thing, that's the final thing. From A4 to A4, we compose now. Instead of 4, we have 6 intertwiners. So we compose these 6 intertwiners to get A4. From A4 to A4. So this is again a self-intertwiner, which is just a complex number. So in this way, so using braiding, we get a complex number arising from this. So this is a new kind of quantum 6J symbols. And here also we have with the braiding operator, epsilon, large, capital E. So this is the kind satisfies the axiom for bi-unitary connection. And this is really the alpha-induced bi-unitary connection. Then we redraw the previous picture. So in the previous picture, we had 6 intertwiners. And in this kind of things, this triple point or crossing represents an intertwiner. So we have 1, 2, 3, 4, 5, 6. So this picture has 6 intertwiners. And this means this picture means the composition. So I draw this picture from the top to the bottom. Some people use the opposite convention, but so this is a composition of this. So composition of 6 intertwiners. This picture represents. So here, for example, this is this part is A4. So this intertwiner is from A4 to A2 times lambda. And this is from A2 times lambda, alpha lambda times A2. This is switch. This braiding means the switching of the two components. So in this way, we can compose 1, 2, 3, 4, 5, 6 things. Then we get, so this picture has no open end. So this is a closed picture. Then by composing these intertwiners, we get a number. So this picture represents a number, which is actually given by the previous diagram. Just a redrawing of the same thing. Then, so this is a number representing a kind of quantum 6J symbol or bi-unitary connection. So this is our picture for alpha-induced bi-unitary connection. But then, so this is rather complicated. But then, so we have some kind of crossing. So after this crossing, here we change the thickness of the wire because this is a kind of NN, this is a kind of MM. So we have different kinds of bimodules, but this kind of thing has been studied by us many years ago. So we can still treat them just like an ordinary topological picture. So here we have overcrossing of this one and also overcrossing this one. Then just like a topology of knots or links, we can move this wire to the right, okay? Because here everything is on top. We can move this one. Then we can eliminate this crossing, and then this move to here. Then here we have a new crossing, and this new crossing here. So just by moving this top wire to the right, we can eliminate two crossings, and instead we get new crossing here. But then this new crossing is just between this lambda and this mu. So here we have lambda mu. So this is the original braiding, okay? But here this is a new type of braiding involving alpha induction. So this is original picture involves some information about alpha lambda plus. So in order to compute this picture, we have to know about alpha lambda. But this is not what we want. We want to have some diagram without involving alpha induction, alpha lambda. This is a new thing. This is actually what we want to know. So without knowing this, we can compute this diagram because we have only this crossing. This is the original braiding. So this is the same picture. So just by compute, here we have 1, 2, 3, 4, 5 intertwiners. So this is the composition of 5 intertwiners. Then just by computing this picture, we get a new alpha-induced bi-unitary connection. So this is our thing. Then here we want to know the role of commutativity of the Frobenius algebra. Then we prove that the commutativity of the Frobenius algebra implies flatness of the alpha-induced bi-unitary connection. So if we do have commutative Frobenius algebra at the beginning, then we get a bi-unitary connection in the canonical form. So two notions, commutativity and here flatness, so they are naturally related in this way. So for proving this, we need to compute the value of this diagram. So now this is the same picture as before, but now here we have 4 objects labeled with iota, the canonical embedding. So here we have the same thing. This is lambda, this is mu. But for 4 objects out of 6, we fix them to be the iota, the initial inclusion. Then we have to show that this is 1. But then the commutativity of the Frobenius algebra shows that we can eliminate this crossing. So we have crossing like this one. Actually, the commutativity of the Frobenius algebra removes the crossing just like this. Okay. Then we get a new picture without crossing. Then we can easily evaluate the diagram. Then basically we get 1 up to some normalization. And also having value 1 is basically a characterization of flatness. So in this way, we can directly compute this diagram. We can evaluate this diagram to get 1, and this implies the flatness. So in this way, we have commutative Frobenius algebra that produces a flat connection. So that was the result I had last year. So this is one direction from commutativity to flatness. But then I now talk about the new thing for the converse direction. So I gave a talk about this result last summer in Rome for the birthday conference of Roberto Longo. And then after my talk, Longo asked me the following question. So does the converse direction of the above result hold? So I explained the commutativity of the Frobenius algebra implies flatness of the induced connection. So how about the converse? So I didn't know the answer last year, and also actually I said the converse was unlikely to hold, but I was wrong. So this is what I'd like to explain today. And the reason I thought the converse was unlikely is the following. So I got evaluation of the previous diagram, and I got the number 1. But then it looked like a kind of a coincidence. It could be equal to 1 just by some another reason, then the converse would not hold. But in the classical case of the ADE linking diagram, so this kind of bi-unitary connection was first studied by Oknian many years ago, and he studied bi-unitary connections on the ADE linking diagrams. And in that case, it's well known that the flatness of the bi-unitary connection exactly corresponds to the commutativity of the Frobenius algebra. But this case was too special because in the case of AD linking diagrams, due to some simplicity of the graphs, we have lots of very particularly nice properties, which is just a kind of coincidence, and we cannot expect them to hold in a more general setting. So the previous diagram could have value 1 just by some other coincidence. That looked completely plausible, and that is why I thought the answer could be negative, I mean, for the converse. But then, yeah, I now recently I realized that converse is actually true. That's the last, right? So I explain finally why the converse is true. So the above argument of flatness, so for one direction of my result, that relies on certain evaluation of some pictorial diagram, as I explained. But this type of argument doesn't give you a proof of the converse because, yeah, just I said, so we want to compute, evaluate some diagram, and then so I so remove the crossing using a Frobenius commutativity of the Frobenius algebra. This crossing can be removed, but this is just a one-direction argument, and this is not the if and only if characterization. So I thought this is impossible to prove the converse using this kind of diagram evaluation, and that's why I was rather negative about the converse direction. But then we can find different, new proof for the previous result. So this relies on the old result of my former student, Nobuya Sato. That's an old result. So actually, we have an inclusion of this kind of thing. So we have, this is an alpha-induced representation, and we use a positive induction here. We put bar, that's like a contra-gradient representation, just like switching on the left and right action. Here, so here we have, so this is alpha bar, alpha, lambda, lambda. Then we use the case power, and we look at the self-intertwiner. This end is a homomorphism from something to itself. And then we can put iota here, the canonical inclusion. So this is a kind of M bimodule. This is N bimodule. Then we have a natural embedding from this, from the left to the right. That's easy to see. But then actually this embedding describes the flat part of the alpha-induced bi-unitary connection. So so I explained the notion of flat connection, but so in general, we have a non-flat bi-unitary connection, but it produces some kind of flat connection as a part of the original bi-unitary connection, and that's called the flat part. And this flat part is exactly described by this inclusion. That's an old result of Sato. Then, so flatness means that here we have equality here. So we are, in general, we have this inclusion, and we have flat connection if and only if we have equality here. So this is an if and only if characterization. So using this, so this is an if and only if thing. So we can use this kind of thing for the converse. Then, so if we have a flatness for the alpha-induced connection, we have equality for this inclusion. Then, in particular, this implies the dimension. So if we have inclusion here, the dimensions are equal, of course. And here, this is we have only one lambda, but we can produce different mu from this construction. So if we have different lambda and mu, so basically the left hand dimension of the left hand side gives this one, and also the dimension of this one gives here. And theta is something called the canonical endomorphism arising from iota. So this have equality. Therefore, all irreducible objects. Then this implies this kind of expression. This is a modular invariant matrix, but then node result of Becken-Hauer-Evans shows that this implies locality. So in this way, that's the commutativity of the Frobenius algebra. So in this way, we can also prove the converse. Okay, so I stop here. Thank you very much.
Okay, so thank you for the wonderful talk, as always. Any question, comment?
Yeah.
So would you like to intuitively explain why the subtle result gives the blank part of the alpha-induced?
Actually, that's rather difficult. This is a quite non-trivial inclusion, and I don't have a good explanation. Yeah.
Any other question, comment?
So in the relation with the two-dimensional topological order, I wonder what, for example, what is an anion in that construction?
Okay, so this anion, so we start with the fusion category without braiding first. Then we have a construction of Drinfeld center, which produces a modular tensor category. So this has a braiding, new category with braiding. And also object there corresponds to anions.
But how do we see that from the four tensor construction?
Okay, so this Drinfeld center can be described with four tensors. So also physicists like Bultink and others, so they have their own construction of anions out of four tensors, but they are exactly the same as our construction in subfactor setting.
Well, I see. Thank you.
Yeah.
Any other question, comment? Now let's thank our speaker again.
Yeah.